first glance, this problem appears to be pretty difficult. But if you start to just kind of read it and circle everything that you have, kind of gather up some things, you'll find that it just is using some of the basic gas law formulas like PV is equal to nRT and Dalton's law, P total is equal to P1 plus P2. So the first thing I'm going to do is look at the problem, and it says that H2 and O2 and H2O. And so obviously I need to write a reaction. And so I know that H2 plus O2 makes water, and we know that reaction. We've used it over and over and over again. And when we balance, we know that we need 2's in front of the H2 and the water. And then I look, and the next thing it tells me is that it's rigid, so I know the volume is constant. So know that the volume throughout everything that we do is going to be 0.5. It also tells me that I originally start at a temperature of 25 Celsius, but again, we have to correct, always in Kelvin, and so we're at 298 Kelvin. Another piece of information it gives us is that the moles of H2 and the moles of O2 in the container are equal. So I know that the N of H2 equals the N of O2. And I know that it's kind of dealing with the pressures, and so I know if my volume's the same and my temperature's the same and my moles are the same, then if I plugged everything to Vp is equal to nRT, then I know my P's would be the same. So the P of H2 is going to equal the P of O2, and that's going to be valuable here in just a second. And then it also tells me that we have a total pressure exerted is 1146 millimeters of mercury, and that they don't give us a vapor pressure chart, but I know that the pressure exerted by water at that particular temperature they give me is 24 millimeters of mercury. So kind of just gathering up things that we know. And so now let's look at A, and it says identify the reactant remaining. So right there, it's a BCA. So I know that I need the before and the change and the after. But I need to know, it tells me my moles of H2 and my moles of O2 are the same. So I know that H2 eventually, that's going to be my limiting reactant because it can't be the same. It has to be twice as much. But I don't know my moles. So I need to do a little side calculation to figure out my moles of H2 and O2, though, that actually match. Well, what helps me on that is this P total. So I know that P total is 1146 millimeters of mercury, and that's being exerted by the pressure of the water and also the pressure of the oxygen and the pressure of the hydrogen, which I know those two values are going to be the same. Well, if I look, I know the pressure of the water is 24. So if I subtract 24, 1146 millimeters of mercury minus 24 millimeters of mercury, that's going to give me the pressure of oxygen plus the pressure of hydrogen. So just a quick simple calculation there, we get 1122 millimeters of mercury. Well, basically, I know these two guys, the PO2 and the PH2, are the same. And so I know, basically, I'm looking for X. I know it's 2X. So if I divide the 1122 by 2, I end up with the pressure of both O2 and H2 as 561 millimeters of mercury. Because like if I pop this in here, 561 plus 561 is going to give me that 1122. Well, now that helps me because now I know a pressure. So as soon as I know pressure and volume and temperature, I can find moles. And so that's what we're going to do now, is I know that Vp is equal to nRT. Therefore, if I solve for n, Vp over RT equals n, and so now it just turns into a plug and chug. My volume is 0.5. My pressure is 561 millimeters of mercury, but notice I need to convert that to atmosphere, so I'm going to divide by 760. I know my R is 0.0821. For atmospheres. And I know my T is 298. So if we cancel everything out, we're going to end up with moles. And so through this calculation, you end up with 0.015 moles. So I know that the N for both oxygen and hydrogen is 0.015 moles. Well, that's what I needed to work all these problems now, because then I'm going to pop back up here, and we're going to enter that on the BCA table. So I know now that my moles I'm not going to worry about the water because it's not asking me for water. If we look, it wants me to identify the reactant remaining. So I know, even without doing any math, I could have said the reactant remaining is oxygen. But then it wants the number of moles of the reactant remaining. So that's why I need to do the BCA. So we know that it's about the hydrogen. So I'm going to write hydrogen moles under both of them. Well, they're both the same moles anyway. But where that's helpful is I know that my ratio is going to be about the hydrogen. So I know the ratio is going to be 2 to 2 and 1 to 2. So obviously this is going to end up at 0.015. So when I subtract this, I get 0. But when I work this out, I get 0.0075 moles. So I subtract that from the 0.015. And obviously it's half of it, so it's the same answer. So there you go. That's my answer to A, is 0.0075 moles of oxygen. So that's my answer to question A, check. So then I look and it says calculate the total pressure in the container at the conclusion of the reaction. So I need to decide, well, what is in my container at the conclusion of the reaction? Well, there's still water vapor, and now there's moles of oxygen. But it tells me also at the conclusion of the reaction it's 90 degrees because they sparked it to make all this go. And so let me just come down here and extend the page. And let's now gather up what we know. So we know we're now at 90 degrees Celsius, which is equal to, we're going to add the 273, 363 Kelvin. We still know that volume is 0.5 liters. And I know that I have some water, and so I'm really just looking for my P total, which is going to be the pressure of the water plus the pressure of the oxygen, because there's no more hydrogen. It's all been used up. It was my limiting reactant. Well, what's really nice is that in the problem, they tell me the pressure of the vapor is 526 millimeters of mercury at 90 degrees, which makes sense. We're getting really, really close to boiling. So we're approaching that 760. So we have 560 millimeters of mercury. But I need to know the pressure of the oxygen so I can add to that. Well, I can find some information. Look what I know. I know that my moles of oxygen that were remaining, remember, were so I know that the N of the oxygen is 0.0075. So I can just instantly do, look what I've got. I can do VP is equal to nRT. It's like if all else fails, do VP is equal to nRT. But in this case, I want to solve for P. So I'm just going to, again, plug and chug. I know my moles. I know my R. Always know R. Know my T now. My T was 363 Kelvin. And I know that V, still remaining 0.5 in that rigid container. So when I work all that out, my moles end up being my pressure, 0.447 atmospheres. So if I add the 0.447 atmospheres over here, I'll get my total pressure. But can I add an atmosphere to a millimeter? And the answer is no. I need to have them the same. So I'm just going to go ahead and convert them to atmospheres. So I'm going to divide this by 760 and then add that to the 0.447. And what I end up with is 1.13 atmospheres. And that's what the total pressure in the container is after the reaction. So that's question B. So this is all of question B. Now the last question, and which is really not like common AP questions, is that C is the easiest question on the whole board. And that says calculate the number of moles of water present as vapor in the container at 90 degrees. Again, let's just kind of go down and what do we know? Well, what do we know? Again, we know the volume is 0.5 liters. Go ahead and change color real quick so we can see. Okay, so volume, 0.5 liters. It hadn't changed. Our temperature at 90 degrees, 363 Kelvin. Okay, I know the pressure exerted. Okay, the pressure exerted was at 560 divided by 526 divided by the 760, which this is actually equal to 0.692 atmospheres. So I know my pressure. So I know V, I know T, I know P. So can we find, this is for water, this is for that water vapor. And so can we find N? Magic formula, Vp is equal to nRT. And again, in this case, we're solving for N again. So we're going to divide by RT. And we're just going to plug and chug. So 0.5 liters. P, 0.692 atmospheres. R, 0.0821. And T, 363. So I always like to double check, a little discount double check to make sure I have the right units. And so if we plug all that stuff in, we end up with 0.0116 moles of water vapor. So a scary problem, but really not all that scary if you just gather up and see what you know. So this is question C.